Hello, I'm Joe Faber. I'm the Global Technology Director at Greenhill Software. Today we'll be talking about developing and deploying critical software in Cortex-A78AE-based systems. So I'd like to address something right off the bat that is a question that I often get, especially from people that are new to safety certified or security certified systems. And that is a misconception that you can't use Cortex-A in critical systems. And I'm here to tell you that this is not a new concept. You know, going back for probably a decade now, people have been using Cortex-A application processors in performance-hungry embedded systems in the automotive space and industrial and avionics. And many of the applications that run on these cores control critical systems and thus have safety and or security requirements. So this is not a new concept. I do run into a lot of people that say, oh, well, you can only run safety critical code on small microcontrollers that have been, that come with some kind of an ASIL certification process or a DO-254 certification process, and that's simply not the case. There are a lot of systems that are out there that are using Cortex-A today, and what we're going to talk about during the course of this presentation is how many of the hardware-based safety features are now being incorporated into the A78AE architecture. So let's start off by defining what is a critical system. It is one where the failure or malfunction may result in death, severe injury, severe damage to equipment and or property, substantial environmental harm, or financial loss. Another question that I get a lot is, what is the difference between safe software and secure software? And at a very high level, and this is really overgeneralizing, but I like to say software is safe when it does what it is supposed to do according to the specification in all circumstances. And there's a bunch of different standards across different industries. You've got IEC 61508 for industrial, ISO 26262 in the automotive space, the EN 50128 for railway, and then, in my opinion, what's the most rigorous standard of all these is the DO-178C DAL-A for airborne systems. And then to contrast that, when we talk about security, we often say, starting with software that has been evaluated for its safety processes, for its safety properties, is a very good starting point, because secure software not only has to do what it's supposed to do, under all circumstances, but you get this additional requirement of, and it is not allowed to do anything else. So it's much, much tougher to make software secure than it is safe, because it's not only behaves as it's expected to, but also doesn't do anything else. And there's a few different standards that are out there. Probably the most widely used one is Common Criteria. In the automotive space now we have the ISO 21434 standard for automotive cybersecurity. And just to give you some examples of how these things are interrelated, more than a decade ago, we did a Common Criteria certification on our Integrity Real-Time Operating System product, Integrity 178. And we started with that DO-178C DAL-A safety spec as sort of the beginning point for what we were going to base our security claims on. And then we developed a bunch of additional requirements, tests, validations, models, etc., to support our security claim. So it was kind of the safety was the starting point, and then adding security to try to prove that this software behaves as it's supposed to in all cases, but also doesn't do anything it's not supposed to do. that was a lot of additional work to make the security claim. And then if you look at the ISO 21434 standard for automotive cybersecurity, it's really kind of designed to, what I would say, it kind of dovetails with the ISO 26262 standard. So as you're going through each step in your process, where in 26262 you might be identifying hazards and ways to mitigate those hazards. In the 21434 standard, you're looking for risks and mitigations to put in place to avoid security risks. And so, again, they're sort of dovetailed, at each step along requirements and design and development and test. They sort of are designed to go together. So I mentioned earlier that safety critical systems on Cortex-A is not a new thing. And I did a quick survey with some of our customers I just wanted to list out a few examples of the kinds of safety critical systems that are being developed today on Cortex-A platforms. And so in the avionics space, both for military and civilian aircraft, we have multiple projects in progress going through the DO-178C DAL-A certification process. These include inertial navigation systems, mission and display computers, and several of these projects are based on Cortex-A53 and Cortex-A72 processors. And again, these are, especially if you look at the like the display computers, these can be kind of performance hungry and yet safety critical systems, which is where we find Cortex-A residing in these safety systems. In the industrial control space, we worked with one of our customers to build an industrial safety controller. That one is based on Cortex-A8. It was certified against the IEC 61508 standard to SIL 3. And there are many other safety and security critical systems based on Cortex-A that we've been involved with in the last several years, including a secure mobile phone that is a really cool design. In the automotive space, there are lots of different driver assistance systems, ADAS systems that are based on Cortex-A. We have customers building medical surgical equipment on Cortex-A with our products, as well as high-speed railway control systems that are also based on Cortex-A. So again, this is not a new thing. This is just a small subset of some of the safety critical systems that we've been involved with our customers, and I know that there are lots more out there like this. So now I'd like to get into what I consider the meat of this presentation, which is what makes the Cortex-A78AE nice for use in safety and security critical systems. And on the next 3 slides, I've got a list of all the features from the 8.1, 8.2, I think 8.3, 8.4, maybe even spec, that have been pulled into the A78AE that are new features beyond what we've seen in some of the ARM v8.0 cores that are out on the market today. Things like the A72, the A53, other things that I've mentioned that are either deployed in products today or are in the certification process right now. And so I'm not going to go through in detail every single one of these bullet points because we only have 25 minutes. So I'm just going to pick out a couple of things that I think are particularly interesting or useful for safety critical development. And the first one is the first thing that's in the list here, which is the split lock for lockstep execution for ASIL-D and SIL-3 systems. This is a hardware feature that gives a lot of flexibility to the designers of safety critical systems. And earlier I mentioned that people have been doing safety on Cortex-A processors for a long time. Even back before they were multi-core processors. So how did they do that on a single core or even a multi-core SMP system running Cortex-A in the past? Well, without support for Lockstep, the safety standards say that you have to address random failures in the systems, things like bit flips or either in DRAM or in registers, just a particle hits the CPU and randomly a bit flips, and your safety case has to account for that. And so in the past, this was largely addressed with something called loosely coupled lockstep, where you would run a pair of either the same algorithms or very similar algorithms, maybe something that was compiled with a different set of optimizations to get you a slightly different implementation in the resulting binary code. But essentially, you run one copy of the algorithm, you run the second copy of the algorithm, then you compare the results. You provide the same inputs, and there are techniques in safety for verifying safe inputs. But then after you run through the algorithm, you come to a point where you then check and make sure that you got the same result. And as long as you did, then you assume that you didn't have any bit flips or random failures in the algorithm. So what the split lockstep buys you is it gives you options. You can now just run the cores in lockstep, very similar to what we talked about that's been available in microcontrollers for years now. But now you have that option at the Cortex-A level. So you don't have to implement that loosely coupled lockstep in your software anymore, or maybe you've been migrating safety critical code from a microcontroller that had lockstep up onto your Cortex-A processor now, and you don't have to go in and add the overhead of doing that coordination at the software level. So that's nice. It simplifies the software a little bit. Anytime you can simplify the software, that makes the testing burden a lot simpler. And this is a very commonly accepted technique for those random type of bit flip failures in the safety standards. However, there's a flip side to it, which is, hey, I've got this Cortex-A core. It's maybe a gigahertz or multi-gigahertz, and I might be giving up that entire core to detect these bit flips when in fact that algorithm that I'm running, maybe it only runs 10% of the time. And so the system designer has a choice to make. Do they want to give up that entire second core, or would they rather continue to use loosely coupled lockstep and have all the extra MIPS that are available on that core to do other processing? And as I mentioned earlier, safety and security, they're both system level problems, and usually with safety there's a lot of extra work that you have to do, whether or not that extra work is the situation that I just mentioned here, where you're running redundant copies of an algorithm and doing comparison, or taking hardware offline to run diagnostic functions. Those random bit flips, you need to continue to make sure all the different hardware in the system is still running correctly, and so doing things like verifying that the MMU is working correctly. You periodically take the system essentially offline and run diagnostic functions to make sure that all the hardware is behaving correctly. And so there's always this trade-off. And one thing that's nice about the A78AE is that if you don't have all that loosely coupled lockstep stuff enabled, you can turn on lockstep in the cores, maybe deploy your first system, but maybe in an upgrade to the system later you decide that, hey, I need the extra performance of that extra core, and maybe you've determined that the algorithms that are especially if you're doing some kind of consolidated system where you have mixed criticality in the system and you've got some safety related code but maybe some QM code or code that is just not safety relevant at all in your system, you might decide that you want the extra horsepower of those additional cores, and so implementing loosely coupled lockstep later, maybe as a phase 2 in your product, is an option, because this lockstep is a boot time configuration where you can either assign the cores to be in lockstep, or you can have the available second core to run with your SMP kernel and get additional processor horsepower. So again, I mentioned that things like diagnostics and a lot of the other safety-related code to meet the standard, it takes CPU horsepower to run those diagnostics, to periodically take things offline, run these checks. So anytime we get performance boosts in the hardware, which you'll see down the left-hand side of the column, I've listed some of these as directly applicable to safety and security features, and others are performance improvements in the core. Those performance improvements are really important too, because in safety systems, you need extra CPU cycles to do safety functions. And so anytime we get a benefit in performance, the next one I guess I'll point out is the CRC, the cyclic redundancy check instructions. CRCs are something that is very commonly used in those diagnostic type functions, whether you're doing safe storage of variables in memory, and there are other use cases in diagnostics where CRCs come in really handy, and it's something that's done over and over and over again. So making that faster and having an instruction that supports it, rather than having a software algorithm that runs every time you want to do a CRC, is a benefit for the overall performance of the system. And like I said, there's some of these features that are safety security related, that like Lockstep, that have an obvious use case in the safety case. But I just wanted to point out that a lot of these performance features are also really useful, because you need that extra horsepower in the system. So continuing to move through the list, and at the top of this slide is actually a continuation from the previous slide, and I probably should have pointed this out there, but there are some new enhancements to the virtualization host extensions that are very applicable to safety certified systems, because the preferred architecture for using virtualization in safety certified systems is to run the virtual machine manager code as an application on top of a safety certified host kernel. And these new extensions are going to reduce the VM entry and exit time by allowing that host kernel to run at EL2 largely unmodified. So this is an architecture that we've implemented with our virtualization products. Very happy to see ARM making these changes to again, it's another performance benefit. Every performance benefit that you can get allows you to do more with your safety systems. So there's several things related to being able to support more virtual machines, some new things in the performance monitoring unit. This is another area in our products where we make use of those performance monitoring counters to help us with bandwidth allocation management, and to make sure that we are reducing the impacts of multi-core interference in safety systems. And so a lot of these features, we at Green Hills are welcoming them. We think that a lot of these things are going to help with kind of our target market and the types of products that we deploy our operating system and virtualization in. So wrapping up the list of the new features for the Cortex-A78AE, the one that caught my eye on this slide was actually the last bullet there, which are the software test libraries. I was talking to our contacts at ARM recently. It sounds like these are not out yet, but they are expected to be delivered in Q4 of this year. in virtually every safety system that we've been involved in, either we or our customers write the diagnostic code for things like the power-on built-in self-test, and also the diagnostic tests that run continuously during runtime. Having these pre-built, pre-certified software test libraries will reduce the amount of time that we have to spend and or our customers have to spend in making those diagnostic functions. So this is another thing that I was very happy to see on the list as being something that's going to be provided by ARM and really helping out the safety critical market. So this is sort of the ultimate question that I wanted to get to is, are these new features that that we've gone through in the last several slides, are these sufficient to deploy critical systems on Cortex-A78AE? The short answer is no, and the reason for that is safety is a system level problem, always has been, always will be, but they are absolutely useful features when you have the right software architecture used in combination with an SoC that implements many of those features. And I mentioned earlier, it really is just giving system designers a lot more choices and a lot more flexibility, and ultimately enabling these safety critical systems to do more. The performance improvements and the kinds of things that the hardware can take care of for you now, instead of having to implement those functions in software. It's a big benefit. There are a lot of factors that go into safety critical development. The overall system performance, the determinism, some safety related factors like reliability and protection. I briefly mentioned multicore resource contention earlier. This is a major factor that our safety teams deal with in certifying SMP systems in avionics and industrial controls and automotive. And the last thing, I know that I'm kind of running out of time in this presentation. The last thing I want to spend just a couple of minutes talking about is this idea of consolidating mixed payloads, including Linux. And that really takes the right software architecture. So what are some of the necessary features of that software runtime foundation in order to support mixed criticality, like being able to have a Linux guest operating system running in a virtual machine alongside safety critical code? Well, the safety specifications talk about freedom from interference, and in order to achieve that, the host OS, typically an RTOS, at least in the case of our product, this is a real-time operating system, that is providing things like time and space partitioning, stack and application isolation. It gives you a capabilities-based security model, which allows system designers to design with the principle of least privilege, which is very good for security. It provides mandatory access control between partitions and devices, gives you information flow control, and importantly makes guarantees about the processor resources to the critical software that's in the system. And I won't go through all the rest of this list, but another important aspect of that foundational software is that it can be safety certified as an element out of context, and also the supplier can provide services to help with the certification of the system in context. So, a bunch of different standards and profiles that we've worked with our products. And then the other thing that I would say is important to look for is something that has already been deployed in safety critical systems to date. So this is what an example software architecture might look like for a critical automotive system based on the Cortex-A78AE. Again, the foundation, I mentioned some of those virtualization host extensions earlier, and that being well suited for having and RTOS as a host for virtual machines, and so we could have a guest operating system like Linux here running on top of a virtual machine monitor, running on top of a pre-certified, up to ASIL D RTOS that is also able to host safety critical applications, security critical applications, fast boot critical applications, and host legacy applications on AutoSAR, for example, whether this be adaptive AutoSAR or classic AutoSAR. And then a very common configuration that we're seeing in a lot of the modern SoCs is that they're going to have the Cortex-A core complex, and then alongside it, and I think my video is blocking this out, but you might have Cortex-R52, Cortex-R82 cores also hosting additional vehicle functions, maybe running on AutoSAR, and perhaps having a hypervisor that's managing those cores for you as well. So this is what we think the future of automotive software architectures looks like in consolidated systems where you have safety requirements, but also the need to pull in lots of different software at varying levels of criticality. And so this is what we think it's going to look like. So I'd just like to thank you all for your time today. The 25 minutes flies by, but I hope this was an interesting presentation for you. I'd be very interested in hearing from any of you. So my email address is on the screen here. And if you'd like to discuss your safety architectures on the Cortex-A78AE or hear more about what we're doing at Green Hill Software on this architecture, we are already actively implementing many of the features that I talked about and bringing up that platform on the ARM Neoverse N1 platform as sort of an early enablement platform. So again, if you'd like to hear more about that or are interested in talking about safety architectures, please don't hesitate to contact me. Thank you very much.